Today, we are going to master advanced logarithmic equations and expressions. By the end of this session, you'll be able to apply the change of base formula and power laws to complex expressions, solve equations where logarithms appear in the exponent, and navigate systems of logarithmic equations. To start, let's refresh our memory on the core laws that we will be manipulating. These are our primary tools. The product rule states that log base b of m plus log base b of n equals log base b of m times n. The quotient rule, log base b of m minus log base b of m to the power of k. And finally, change of base log base b of a equals log base c of a divided by log base c of b. In advanced problems, the challenge usually lies in recognizing which law to use when the bases are different or when the variables are nested. Our first challenge involves expressions with nested logarithms. This requires a systematic inside-out approach. Our goal is to simplify the expression log base 2 of the log base 3 of 81. Let's look at the inner part first. Log base 3 of 81. We ask ourselves, 3 to what power equals 81? 3 to the power of 4 equals 81. Therefore, log base 3 of 81 equals 4. Since 3 to the power of 4 is 81, the inner logarithm simplifies to 4. Now, we substitute this value back into the original expression, 2 to the power of 2 equals 4. Now we evaluate the log base 2 of 4. Since 2 squared is 4, our final answer is 2. Notice how we broke a complex multi-layered problem into 2 simple steps. Whenever you see nested logs, always start from the innermost parentheses. Now, let's tackle a common hurdle in advanced exams: solving for x when the bases are different. Notice that we have base 2 and base 4. To combine these, we must make the bases identical. We will use the change of base formula to convert everything to base 2. We know that log base 2 of 4 is simply 2, because 2 squared is 4. Or, writing it another way, 1/2 times log base 2 of x. Now, let's rewrite our original equation using this substitution. By combining the terms on the left, 1 log plus half a log, we get 3/2 log base 2 of x. To isolate the logarithm, we multiply both sides by 2 and divide by 3. This simplifies to log base 2 of x equals 4. Finally, we convert from logarithmic form back to exponential form to find x. Calculating that gives us our final answer, x equals 16. By converting to a common base, we turned a multi-base problem into a standard linear-style log equation. Next, we will look at a more complex scenario: equations where the variable x appears in both the base and the argument, or within a nested exponent. Our goal is to solve for x to the power of log base x of 5, all squared, equals 25. This looks intimidating, but we can use the fundamental identity of logarithms. Remember that b raised to the power of log base b of y is simply y. Applying this to the base of our exponent, x to the power of log base x of 5 equals 5. The term inside the parentheses simplifies beautifully to just 5. Now we rewrite the equation. 5 squared equals 25. In this specific case, the equation simplifies to 25 equals 25, which is an identity. This means the equation is true for all valid values of x. However, we must remember the constraints on a logarithm's base. The base x must be positive and cannot be equal to 1, so our solution is all positive real numbers except 1. Let's try a harder one where we actually solve for a specific value. Solve. 3 to the power of x equals 5. When the variable is in the exponent and the bases cannot be made equal, we take the log of both sides. Usually, natural log or log base 10 is easiest. Using the power rule, we bring the x down to the front. Now, divide by the natural log of 3 to isolate x. This is the exact answer. If you need a decimal approximation, you would use a calculator to find that x is approximately 1.465. Finally, let's explore a system of logarithmic equations. These often appear in advanced calculus or competition math. Our goal is to solve the system for x and y. Equation 1 is log base 2 of x plus log base 2 of y equals 5. Equation 2 is log base 2 of x minus log base 2 of y equals 1. This system is set up perfectly for the elimination method, similar to how we solve linear equations. Let's add the two equations together. Adding the equations, the sum of the left sides equals the sum of the right sides, 5 plus 1. The positive and negative log base 2 of y terms cancel out, leaving us with 2 times log base 2 of x equals 6. Dividing both sides by 2, we find log base 2 of x equals 3. To solve for x, we convert this to exponential form. 2 to the power of 3 is 8. Now, we substitute log base 2 of x back into the first equation to find y. This gives us 3 plus log base 2 of y equals 5. Subtracting 3 from both sides, we get log base 2 of y equals 2. Again, converting to exponential form, y equals 2 squared, which is 4. Our solution is x equals 8 and y equals 4. Let's check our work. Log base 2 of 8 plus log base 2 of 4 is 3 plus 2, which equals 5. Correct. And log base 2 of 8 minus log base 2 of 4 is 3 to 2, which equals 1. Also correct. Always check your answers in the original equations to ensure they are within the domain of the logarithms, meaning the arguments x and y must be positive. In this case, 8 and 4 work perfectly. To summarize what we've learned. First, simplify nested logs from the inside out. Second, use the change of base formula for different bases. Third, take logs of both sides when the variable is in the exponent. And finally, use elimination or substitution for systems of equations. We have covered the most common advanced logarithm patterns. Practice these techniques, and you'll be well prepared for any complex logarithmic problem.